Okay, we're going to start the next big topic in class today, which is trajectory optimization. I think some of the ideas are very easy, but there's lots of different variations, and I'll try to make it interesting with some examples and case studies. Let me just make sure I say clearly, the midterm is next Thursday. It's in class. It'll cover the material through this week, which is also the material that you'll have had a problem set before the midterm. Yeah? And we're going to post on Piazza very soon sort of the practice exam and what you can have in terms of a sheet of notes and all that, the logistics side of that. Okay? Okay, so why, we've been developing a lot of tools. Why do we need a new one, right? I try to only bring new tools if they're going to bring new capabilities or solve some problem that we can't solve yet. And so let's just maybe start again with a little bit of the big picture. Right, we've been talking a lot about different optimal control approaches based on dynamic programming as the heart. Dynamic programming, the idea, underlies everything we've done, I would say. It's kind of like almost synonymous with optimal control. We've understood cases where we could sort of do tabular solutions exactly or mesh-based approximations. We talked about some beautiful solutions that had closed form, right? Solutions, LQR kind of solutions. We talked about the function approximators, so let's call it neural networks these days. Okay, and just to say it again, right? The tabular works beautifully. We can converge fast, very efficiently to an optimal solution. The only way that it really dies for the problems we care about is that making a mesh of a high-dimensional state space and state action space becomes computationally intractable. You have the curse of dimensionality. The number of mesh nodes you would need in high dimensions grows exponentially with the number of dimensions. LQR goes to sort of arbitrarily high dimensions. We have almost closed form solutions. There's a numerical recipe that scales extremely well to solve the Riccati equation. Its only failing so far is that it's restricted to linear systems, and we talked about, when is that a good assumption. Now we even have tools to sort of find the boundaries of when that's a good solution by, let's say, using sums of squares and Lyapunov. Neural nets can potentially go the distance in terms of scale, in terms of high dimensions, but these require some, the way we've presented it, we need some sort of sampling distribution. And I haven't given you any profound recipe for that yet. If you say you need to sample uniformly over the state space, then you're just as bad as the tabular case, right? So we'll have more approaches to that as we get into RL, okay? But you need some sort of a sampling distribution. And typically, once you get to the higher capacity nonlinear approximators, then you've lost some of the guarantees of convergence, right? And ability to analyze things. And then we started talking about Lyapunov, right, as simpler than DP, than optimal control, let's say, but because we relaxed the equality of the cost to go into an inequality in the Lyapunov conditions. And I gave you a few more computational tools, like the sums of squares optimization. I guess we ended a little abruptly with that. I didn't really tell you how much this scales, okay? But this is actually a very nice solution that gives us some of the guarantees that we enjoyed in the closed form solutions. When it works, right? When we're able to find a polynomial certificate, we have guarantees. And I would say this goes into the tens of dimensions. Let's say 10 to 20 dimensions. It's complicated to summarize it because it depends on the degree of the polynomial, the degree of all these things, okay? But let's say you can get into the tens, whereas with sampling we said you're stuck around 5, okay? Maybe more if you make SOS approximations. You can give up on the positive definite constraint, make a linear programming approximation of it, and you can get to higher and higher dimensions. Okay. And actually, even though I introduced it in the context of Lyapunov, you can do approximate dynamic programming. I decided to not spend a lecture on it, but it's in the notes if you care, right? You can do approximate dynamic programming with sums of squares. You can, the same way we did linear programming, dynamic programming. You pushed up on the bottom of the cost to go with linear constraints. You can push up on below a cost to go, polynomial cost to go with sums of squares. And actually that is a very elegant solution. It can be numerically challenging. If I thought it solved everything today, I would tell you, I would spend a lecture on it, but it starts getting into SDP complexity pretty quick. So I think that we should continue to evolve that set of tools. Okay, but I think all of these, in my mind, and maybe we mentioned it a little bit here, the sampling distribution, we're always fighting the curse of dimensionality. Every one of these, it's like we're getting farther and farther trying to solve this really hard problem, which is we have some big state space. We want to have a policy and a cost to go function over the entire state space. And that is just hard. And the bigger the state space gets in terms of dimensionality, it's going to grow hard. It's just going to be hard, right? Except for the cases of where things are quadratic or something. There's some very special cases. But that's just a hard problem to say I've got a policy that works for all possible initial conditions. So today we're going to go to the opposite extreme. We're going to throw that out completely, and we're going to say I want a policy, if you will, a plan that works from just one initial condition. Okay? That's where we go from policies to trajectories, and it's the most fundamental way we have to sort of break the curse of dimensionality. Forget about all x. I'm going to care about one x. That's the name of a company now. Cool company, but not what I did not intend to, call them here, summon them. Yes, I just want one dimension, which is time, and I'm going to write everything in terms of sort of just one dimension, right? And so, I think it's related to the sampling distribution point, and I've made this point a little bit before. But if I think of myself as a humanoid robot, okay, I have lots and lots of degrees of freedom. It's hard to even count them, right? If I were to discretize my state space, there's not enough time in the universe for me to visit all of my states, right? It just, even a modest number to the exponential, number of degrees of freedom I have is astronomically big. Yes? Yeah, that's even more, right? And I know they're not exploring the whole state space. Yeah? Right? Right? So so somehow asking things to work for all x, although it's beautiful, it is wrong, I think. That it's too much to ask, except for in very simple models, right? So we sort of have to give that up. Okay, so today we're going to go for all x, which we've been doing, to just say I want a solution for just one particular initial condition. And I'm going to think about the path that the optimal controller takes when I start the system in that one initial condition. Okay, and that fundamentally allows me to not have to worry about the curse of dimensionality. there's a couple other sort of nice things to think about here. So just even in terms of numerical methods, like we know a lot about numerical analysis of solving PDEs in high dimensions and things like this. There's a lot of tools you can bring to bear, but we actually know a lot more about the single dimensional. Like everything's better in one dimension. You could sample if you had to. We have error-controlled integration. We know tight results for polynomials in one dimension. Like everything's kind of easier and better in one dimension than n dimensions. So you'll see some extra maturity in some of the methods. Okay, so what I want to do is I want to introduce the world of trajectory optimization to you. I'm going to start like I like to do in the simple problems. I'll start with the linear discrete time case. That's the simplest case. It should be super clear there, I think. And then actually, if you get that completely, then the nonlinear cases follow very, very naturally. Like they actually don't take much time. They take a lot of time to fully master, but to get the core ideas across is actually very simple. So let's start with linear discrete time trajectory optimization. Everybody calls it traj-opt. Okay, I think in my chapter notes are even traj-opt.html. Right? Okay, so here's the optimal control problem I want to write down. First, I'm going to choose a finite horizon. Oops, finite horizon length n. Okay, so where we've often talked about infinite horizon optimal control, we're switching in trajectory optimization to thinking more fundamentally at a finite time because we want a finite number of decision variables in time. Here's the simplest way to write that down. So I'm going to use this as shorthand for my decision variables are x0, x1, all the way up to xn. Okay, and this one, actually for u, we only need up to un minus 1. Okay, but that's my trajectory of decision variables of x, just a finite list of decision variables. And I'll take the sum of the costs, because I'm in discrete time. In the finite horizon cases, you'll often see that we'll add in a final horizon. If I do something like this, this could be we call this a terminal cost. And I'm going to write this as subject to the dynamics, my linear dynamics. I'll write it as a constraint, just to keep the notation clean. I'll just say that the first x is actually constrained to be the initial condition we care about. And then I could put a bunch of other constraints on here. I could say, for instance, maybe u is bounded between 1 and -1 for all n. Or I could write other costs and constraints here. That looks a lot like what we've been writing always for dynamic programming, except this time I mean it extremely literally. Like, I am going to write a mathematical program. It has finite decision variables. I've enumerated them here, x0, x1, and n, one for each time step. Okay, I'm going to call prog.new decision variables, new continuous variables, right? And then I'm going to have my dynamics written as constraints. In this case, that'll be linear constraints on those decision variables, right? That's another linear constraint. That's a linear constraint. Okay. So it makes sense to, for instance, choose, since I've got everything looking linear down here, often we'll choose Lx U to be, for instance, a convex quadratic constraint. And if we do that, if we make that choice, for instance, then we have linear constraints, a quadratic objective, a convex quadratic objective. Then we can solve this trajectory optimization problem as a quadratic program using convex optimization. Okay? So what does that mean? That means, this is one of the convex optimization where we have really good solvers. And it means that if I put in a problem here that doesn't have a solution, the solver will actually say infeasible, right? I overconstrain my, the dynamics cannot, for instance, satisfy all the constraints for any U. I could get infeasible from the solver. Otherwise, I'm going to get the global optimal solution. This is a good place to be in terms of optimization. You could put this on an autonomous car or autonomous plane and be okay with it because the solver is going to give you the right solution, guaranteed, or say infeasible. You don't want your autonomous car to say infeasible, but you can carefully avoid that, and that will be something we'll say in a little bit, how to guarantee that you have recursive feasibility. Okay, so that's like a little bit different than the optimal control problems we've been writing. Right? How does that compare? Why would I want to solve, like the way I did it, it looks a lot like LQR, for instance, right? So why would I want to solve a quadratic program instead of just get a closed form solution for LQR? Let's just compare this versus LQR. LQR had the Riccati equation. Now we have a quadratic program. That seems worse, but it's not bad. QPs are really tractable. In general, you can solve very big QPs very fast. Okay. We've got a finite horizon versus infinite horizon. That's a difference. But if you read the notes carefully, you notice that there is a finite horizon solution to LQR that's also solving a Riccati equation. Okay. So it's not really a fundamental difference. I mean, it's going to be fundamental, but we're going to walk and make that difference kind of disappear as we go through it. There's a huge difference. What's the huge difference? The essential big difference that motivates solving QPs. Yeah. Yep. Yeah, exactly. That's the huge motivation. In fact, what you should think of is, I think it's generally accepted that if you want to solve a constrained LQR problem, okay, then solving a QP is kind of the way you solve constrained LQR problems. Right? If you have input limits or state constraints, we'll see a few examples of them in a minute, then this is the sort of the right way to do it. And that's new, and that's important. In fact, there's a whole line of work, which you'll understand the name of it in a little bit better in a few minutes, but if I were to take, let's see, the difference between solving from a single initial condition and solving for the policy you can kind of go back and forth between them, right? If you have a policy, of course, you can simulate that policy from one initial condition and get the trajectory. The other way is much harder, but for making plots in a few dimensions, it's possible. I could just evaluate I could solve this optimization from every single point on my graph and plot the policy, okay? And if you do that, there's actually more elegant ways to do that. If you do that for like LQR on the double integrator with constraints, then the optimal policy looks like this, okay? This is with n equals 8. You already get, so we know a lot about, there's a mathematical basis of this. It's called explicit model predictive control. I don't want to get into that just yet, but we know how to compute the solution beautifully and exactly, but it only works for small state spaces because the actual solution is complicated. It has all these faces, and the number of faces grows very quickly with horizon and state dimension. So, in fact, so the way to think about this, the yellow solution here of trying to get to the origin is going to be the solution that is equivalent to the unconstrained case, where no constraints are active. I solve the trajectory, and U is between -1, strictly between -1 and 1 for the entire solution. And every one of these faces is a different active set of the optimizer, okay, where basically for one of these, it might be that you're up against your constraint at time 3. And this was like at time 4, or time 3 and 4. So every different permutation of you ran into some constraint, and the solver had to give you a different smooth solution. The changes of when you hit or release from a constraint are what makes the non-smoothness in this. And inside, having the set of constraints the same, it's actually a smooth linear control policy. Okay, so we know a lot about that. But the point is, this is actually a pretty complicated optimal policy, but we're representing it perfectly, implicitly, not explicitly. Solving it for every state would be the explicit solution. But we're solving it implicitly, like in order to evaluate the policy at any state, I have to solve an optimization problem. I have to decode it in order to pull out the solution. So did I make that point? Okay, like it looks like a small addition. I just threw in U equals -1, but we're actually computing a very rich new object, much more complicated policies. It's very tractable because we're computing them for only one initial condition. Yeah. If you can make that graph, you can. It's just that you can't make that graph for big problems. It's like worse than value iteration in terms of, it's more exact, but it scales very badly because it scales also with the horizon length.
Can you pull out like an algebraic formulation policy, like LQR?
So I think the explicit MPC, there are toolboxes that will try to compute the explicit solution. They just don't scale to big problems. But the explicit MPC world is trying to compute the solutions, explicit solutions to these optimization problems, has given us a lot of theory, like a lot of understanding about what the shape of the optimal solutions look like. And there are approximate explicit MPC algorithms that try to approximate that with less faces, for instance, and come up with more closed form solutions. An extreme of that would be to try to find the closest smooth approximation to that. Maybe that's kind of what I heard you asking. Yeah? So that I would call that like an approximate explicit MPC approach. You could get to it from a handful of different ways. Yeah, we might come back. I don't want to dwell on that. I just want to say, just help you understand that something complicated happened there, even though the math looks very simple, right? I called this linear trajectory optimization. It's often called linear model predictive control, linear MPC. I'll talk about MPC before we're done with today's lecture, right? Some of you know what it is already, but it's so common to solve this in an MPC loop that people call it linear MPC instead of even calling it linear trajopt. Okay, but you could think of it either way. Okay, so let's think for a moment about this, the finite horizon case, okay? It's hard to solve if the, the number of faces in my solution changes with the horizon, okay, then clearly there's some dependence on time. And if I make this very big, I get more and more expensive optimal control problems, okay? But there's a nice thing that happens here, and you can sort of see it in this picture. So here's an idea. Let's take the final cost, the terminal cost, okay? I'll just write it like this. There's no end there. Okay. Here's one way we can walk back and forth between finite horizon and infinite horizon. Just 1 second. Right? So what if you said that, if I think about this optimization problem as if big N was 0, then my cost function is basically just the LQR solution. My solution would be the LQR solution. But when I read this, if I were to insert that right there, what I read is solve the constrained problem n steps into the future. And then to get from n to infinity, I'm going to just take the unconstrained optimization and assume that's a good approximation of the rest of time. Okay? Is that kind of second? Yep. Yep. Well, we also have Riccati equations for the finite horizon case. So yeah, the algebraic Riccati equation is the steady state, but we also have a Riccati difference equation that would back up and do the finite horizon case. So they're both Riccati equations. If you were to keep all of your problem data the same, then actually if you take the discrete Riccati equation, the Riccati difference equation, and back it up as time goes to infinity, it will converge on the algebraic Riccati solution. So the finite horizon is different when you have a time limit. When you really the bank closes at 4 p.m. or whatever, then you can get different solutions. But if you have, as you bring the horizon, and that would be true here too, is that as the end, if you had the unconstrained version here, if you just wrote the QP and you took n and ran that to infinity, you would get closer and closer to the unconstrained LQR problem. And so kind of a nice way to mix them back and forth would be to say, I'm going to do the best I can understanding the constraints for n steps, and then assume that I don't have constraints for n till time goes to infinity. And this picture sort of suggests that that's maybe not a crazy thing to do, right? When I'm close to the origin under like a linear trajectory optimization kind of framework, then often you don't need the full control authority to get there with a quadratic objective. So if you think, I'm going to get here into the yellow region in n steps, and then use the yellow region as my solution for the rest of time, then that's actually a pretty reasonable thing to do. That's very problem dependent, but that's kind of the intuition behind it, right? Is that this is a reasonable approximation. It's an optimistic approximation because it's the unconstrained version, and added constraints only makes it harder, okay? But it's a nice way to kind of take a finite horizon trajectory optimization and make it think about things, its infinite horizon consequences, at least partially. Okay, but this ability to sort of add constraints really does change what you can do with the problems, right? So With LQR, we just wanted to get there exponentially, but we don't actually have finite time convergence to the origin. We find like u equals negative kx, that'll just get there in an exponential way, but it, it converges, but it doesn't arrive in finite time. So you could, in the, now that we have these language of constraints, you could also add state constraints. You could say, I have a terminal constraint on x, saying I want to be there at time n. Absolutely, right? So for instance, you could write a different sort of similar optimization. Could be, let's say, maybe I want to just minimize effort subject to x0 equals x0, xn equals maybe 0, like x final, x desired, okay? And then, of course, the dynamic constraints. You could say that's another way to write. I want to get to the origin. I want to use not too much energy while I'm doing it, but I want to get there absolutely in capital N steps. And we couldn't have written that before, right? But that becomes available now. Yeah. So, okay, good question. So what is the relationship between this and the optimal cost to go? So this is an optimization problem. It's trying to solve for the optimal trajectory and the optimal state trajectory and input trajectory from the initial conditions. The value of the solution, like the cost that is obtained on that trajectory, will be the cost to go from that initial condition. And the first action will be the policy, if you will, from that initial condition. Right? So that's maybe the relationship to the whole thing. But we have the solution figured out exactly along one line in through state space. Finite trajectory section. Okay, so we can play with this kind of thing. This is, in fact, let me just write it. So you can write these things very easily in in the language of mathematical programs. I can just make n-1 continuous variables for u. In the double integrator case, I have x is two-dimensional, so I'll have a 2 by n matrix for x. I can add bounding box constraints to say that my initial condition is fixed. And then I can add my dynamics constraints, add a bounding box constraint on u, and I add a little quadratic cost on u, and then a final value constraint, solve, right? And this thing, mathematical program will realize that you've only ever added linear bounding box convex constraints, and it will call a QP solver for you. Yeah. Good question. So why did I make x a decision variable? Couldn't I just solve that away? Yes, I can, and I will do that next. Great question. Yep. This is called maybe the most direct. It's called the direct transcription, but there are multiple ways you could write it down. Yeah, you'll see. Okay, so there's lots of different things we can do with this. Of course, you can run it too. Okay, so someone asked the other day about, are there tricks to writing optimization problems and the like? And I do think there's like a skill that you build up of formulating optimization problems, recognizing them to be convex when they're convex and not, right? So, but this sort of gives you a new rich palette for writing costs and constraints on the trajectories, right? You could write constraints for all n. You could say I want to have u. I have limits on u for the first 3 steps and then not afterwards. There's all kinds of variations, right? We chose quadratic costs here if you were to write, for instance, sum over, let's say, just x, absolute value of x, maybe with an absolute value of u, for instance, like the different objective, that would be an L1 norm objective, right? Just taking the absolute value if those are scalars. And that would give you, that's a linear objective, it turns out. It looks like an absolute value, it looks nonlinear, but you can write that down as a linear program. And there are a bunch of tricks, and I try to mention a bunch of them in the notes, and I have a dream of writing all of them down in the optimization playbook appendix, but it's pretty empty right now. It's like I'm working, I never quite finish it, but there's a lot of good tricks. But you've got a new sort of canvas to play with. So if you have this canvas, how would you solve the min-time double integrator? Given this sort of, this set of, what costs or constraints would you write to try to solve that? Do you remember? You remember the problem, right? It was q double dot equals u, and then u let's say equal to 1, and I want to get to the origin from some particular initial condition now in the minimum time. Is there a way to write that? Ideally, a convex optimization way to write that. Yeah. If you did that, then you're going to, I think you're right in the sense that it would allow you to go to the limits if you did that, if you removed this. But that is not quite the time objective. Really, you just want the objective to be 1. If you just want to minimize time, for instance, yeah? Maybe that's kind of what's happening here if we did that. Yeah.
Could your large n be an optimization variable?
That's a good question.
And then sum up just ones.
Right? So I wanted to make that point explicitly. So we came into this, we chose the large n. Can we make it an optimization variable? And the answer is actually not with convex optimization. But the good news is it's a discrete variable and it's a scalar. And our convex optimization solvers are so darn good, right? They say, yes, I found the optimal solution, or no, no solution exists. Okay? And we know that if you choose n big enough, then there will be a solution. If you choose n too small, you're not going to be able to get to the final. If you put a final value constraint, you won't be able to get there. It'll say infeasible. So here's how you use convex optimization to solve the minimum time problem. You go up until you find, you choose an n that's big enough that it gives you some trajectory that gets to the goal. And then you make it smaller until it fails. And you found it. You can do golden section search or whatever, okay? And you can do that because these things are so robust. Like you don't have to worry about the solver getting stuck in local minima or whatever. You know, it's just going to say, nope, I can't solve this problem, and you know you've gone too far. So I did that here. It's kind of interesting, actually, to look at it. So here is the discrete time solution. I did a little line search manually, and I found n equals 284. Okay? And just as a sanity check, I looked at the true solution, which I only have for the continuous time, and this is discrete time. Okay? And the true solution was, it should take 2 square root of 2 seconds, which was 2.828 seconds. Okay? And I had a dt of 0.01. So that seems to check out pretty nicely, almost. Like, there's a gap, right? So I got basically 2.84 seconds, and I wanted to get 2.828 seconds from the continuous time solution. Yeah. I did mumble that. Let's think about it carefully. So in the way I've written it, it would actually change the number of decision variables. So that's like out of bounds. I need to come into my mathematical program and declare some number of decision variables. I can't ask it to change the number of decision variables. So if you were to go farther and say, well, what if I made some decision variables, but they like went to 0? You can't do that carefully in a there's a lot of different ways you could try that, but you'll always run up against some non-convexity every time you try that. Yeah.
Why this
But they're all linear. The constraints are all linear affine constraints in the decision variables. So they form, because it's the union of linear constraints, it's going to be a polyhedron, which is a convex set. So we have good methods to find the interior of that set. So you don't have to have an initial guess, basically, and it's easy to stay inside that set once you're in there. Yeah. Yep. Yep. For sure. Yep. Yeah. That's part of the reason I wanted to give that as an example, is because the mindset should be here. You can solve these fast. You can solve them at a kilohertz if you need to, in a control loop, right? Okay. You could try something that was a really hard control problem and make me wrong about that, but like big problems can be solved at hundreds of hertz with these kind of solutions, for sure. On Atlas, we were just solving QPs at 400 hertz 10 years ago. So without bringing in like all the special purpose codes that people would really do to make that super fast. So for the example I gave, you actually don't need a cost function. You could just say, find me any solution, find me an x and u, for the x0 is at my initial condition, x final is at the origin, u is always inside the bounds, and it'll say true or false. The cost doesn't actually matter for that search. Good question. Yeah.
What are like in the sense of like, this seems like it's something that's kind of clever that can work nicely.
Yep.
But it also seems like the kind of thing that might drive some people crazy.
Okay. I'm good with that.
But
Yeah.
I mean, it seems cool.
No, I think you're right. So we'll see even in just a few minutes, maybe at the bottom of this notebook, one that might be more generalizable and it'll drive people crazy in a different way. Yeah. Yeah.
Probably jumping ahead, but how do you handle constraints that change
Carefully. So you can do that. Sorry, let me understand. So in a single optimization, if you had constraints that are different for different n, that fits in fine. If you're running this in the loop and the constraints are changing like if I'm an autonomous car and suddenly I saw a tree that I didn't see in the previous frame, then you have to be very careful, because you don't want to have all of your solutions become infeasible. And you work very hard to try to always be able to hit the brakes or swerve or something like that. Yeah. But if it's the simple case of just like a priori, I know that at time 3 this constraint turns on, then that just fits right into quadratic programming. Good. So can we understand the little gap there? It's important, I think. So why did I get 2.84 instead of 2.828? Or at least 2.83? Because I discretized in time 0.01, but why did I get 2.84 instead of 2.83? It's kind of annoying, right? Then to be clear, the min time solution I'm talking about is for the continuous time system. Yeah. Yeah. So let's look at how there's multiple places where you could be doing a discretization error. Okay. So I'll do it for a general linear system, even though the double integrator is a particularly simple one. But in general, I went from this to something like this. Okay. One way to do that be to say this right-hand side is just like an Euler integration, okay? Let me do discrete B and continuous, just to not confuse those two. Okay, this would be like my time step, my delta t, if you will, right? This would be like the Euler integration. And if I do that, then I have some integration and approximation error, for sure. You don't have to do that. For discretizing, time discretizing a linear system, you don't have to do that. You can actually use AD is e to the ACH, for instance. You can have an exact exact discretization of continuous time systems. It happens I did this, but that's just I was lazy. I should have done this. Right? This is where I used a more generic code because I wanted to also work for nonlinear. But for linear systems, there doesn't have to be a gap because of that discretization. But there is still a gap. And it's the way I've parameterized U. Okay? So I can, given a U and an initial condition, I could integrate it perfectly. But I've only parameterized U as kind of the zero order hold of the possible inputs. I've only searched over, time, U of time. Right? I've only given myself the ability to sort of change U at these finite intervals. And I could choose a different integration and try to integrate it perfectly with knowing what I know about linear systems. But we've picked some finite parameterization of the input. This is like my U0, U1, U2, okay? And the mindset I want you to have around that is that I'd love to search over all possible curves UT. If I've only parameterized this set of curves, that's like I've added constraints. There's the perfect class of curves, and now I'm constraining myself to a subset of those curves, which are the ones that can look like a staircase. So the cost only goes up. When you add constraints, you only find a slightly worse solution. So my time needed to go up, and it went up because of this, most fundamentally, okay? So think of that as like this zero order holdness decision, or if I did a first order hold or whatever, that's a decision that limits the class of curves and will increase the cost. Yeah. There's no quantization error per se. It's continuous. I'm searching the continuous values in U up to the numerical solver tolerances. So that one, it's going to get to almost 1 and not almost 1. Okay, so and if we look at this, the way that plays out, right? So you see that? So it's at what's the true optimal solution would be bang bang, right? All ones, all -1 in this case from that initial condition. But it took its time getting down to -1. And that's because of this sort of zero order. Well, I mean, okay, I drew it as I should have drawn it more as a staircase. It would have looked like here. There's a point here in the middle. I'm going to change that plot when I get home. That's not consistent with the way I chose to present it. Okay, there's a little slop in there because of that. Yeah. You are eating a lot of bananas. I hope you're good. Yeah. Sorry.
Yeah. I would see that you lose. I would see that the zero order hold at some cost when you're doing something intricate where the optimal solution would actually be a continuous curve.
Yep.
Or a smooth curve.
Yep.
But in this case,
great.
I mean, the optimal solution would be a
good.
non-smooth curve, and I don't see why you end up with a non-smooth one now.
Good. So what is the optimal switching time is the fundamental question, okay? if the optimal switching time lands exactly on one of the time steps, then you could have zero loss. I completely agree. That's and yeah, but we're not that lucky. In fact, it'd be very unusual, I guess, to have the switching time land exactly at one of those intervals. So it's trying to like cut the corner there. Yeah.
There's no constraint on how, like the acceleration.
There's no constraint on the acceleration of
So
u.
it can go instantaneously.
That's right. Yeah. Real actuators, no. Mathematical model, yes. Okay, so let me just show you that, right? So if I were to take this and make that 283, for instance, it says optimization failed, result success is false, right? It just says infeasible. This is what I want. This is what my solver to just say yes or no, right? If I were to go higher, then it actually takes its time to get down there. That's also because I snuck in an object. I don't like leaving things fully unconstrained. I snuck in a little u that shouldn't matter into the objective, but okay. But for 284 is the smallest number that I can find a solution given that discretization. So that's an upper bound on the cost to go. If you're happy locking in n, so if the time is not a decision or an objective or a constraint or whatever, I think if you're willing to lock in n, then things can be just one-shot convex. Yeah.
What if you're not as concerned? I guess would it be unfeasible?
Like adding these, I think the finite time plus a terminal cost is a really nice recipe to be able to specify a lot of things like that. Let's do it. I think it'll make it look more different if I extend it. You guys can do this too. I hope when you're reading the notes carefully, right? It just it makes things a little bit more messy. I think there's a kind of a null space of solutions that can average, right? So what matters is the total integral result of this control, and there are multiple solutions, including chattering ones, that could total sum achieve the same result. I like this better. Yes, typically you would do that by having, so you want to use, if you stay in the additive cost, you would typically introduce additional decision variables and say that my u dot, let's say, is a linear combination of my two u's, for instance, and then you can keep additive cost on those new decision variables. And adding decision variables is cheap in QPs, for instance. Yeah. Okay, so this formulation looks weird. I've got an x, right? You asked the right question, right? So why do I don't really need this x, right? So the way, I could solve that away. You made exactly the right observation. So that's one transcription. It's called the direct transcription. Classically, that's the name for it. So when I say a transcription, I want to take my mathematical problem and transcribe it into a numerical recipe. Okay, so the step of taking sort of the math and turning it into decision variables and costs, that's the transcription. And the one we did is this direct transcription here. Where we have decision variables for both x and u, and then we have constraints that are for the dynamics, that enforce that those are the same. There's another one that's called direct shooting, or often just shooting. There's a whole class of trajectory optimization methods that are the indirect methods too. This is not superfluous. It's actually saying it's not one of those other indirect ones, but we don't use those so much. Okay, and so the direct shooting method, it would have decision variables only if you're given x0 maybe, or if you can make a decision variable and then just u. Why? Because, especially for linear systems, I can always write x of n as a to the n x0 plus, what is it? It's always k, k to the n, and it's n minus k minus, which one is it? N minus k minus 1 times b u k. Right, that's just x0 is x0, x1 is a x0 plus b u0, x2 is a times that whole thing. Right, you just add that up. It has this nice pattern that emerges. It's a minus n minus a to the n minus k minus 1. Okay, and the great thing is, this whole thing, right, is still linear in u. Right, and if this was a decision variable, fine, that's linear. So those are still linear objects and compatible with our optimization. In fact, you don't even need you don't need to keep this as a constraint. You could just insert this directly, right? If I have now min over u, some of, let's say, xn q xn transpose n r u n, I could just substitute this whole big thing everywhere I saw xn. I don't even have to write that as a constraint. I can have an unconstrained optimization potentially, unless you have other constraints. I could just solve away x. It doesn't need to appear. Given x0 and u, it's completely specified. I think that was your point, yeah? So that seems good, right? That's called the direct shooting method. It has less decision variables, less constraints. Seems only good. It's not only good. There's some cases where it's better. There's some cases where it's not better. So what could be wrong with it? We're going to have you explore this a little bit, I think, on the PSET. But the one thing that goes wrong with it is you end up taking a to the big power, potentially. So it can be numerically a little bit more finicky. And that's sort of real. Like let's look at this one, for instance, right? But the effect that a u can have that u at time 0 has on x at time n can be very big compared to what the one just before it had. It has more time to act. This is not like a problem with our math. This is the truth of dynamics, is that you have lots of time for your system. If this is unstable or close to unstable, then this can be big. If it's stable, then it could just damp away. So it's numerically different, and we'll make you explore that on the problem set, okay? It also, there's a lot of subtle reasons. Like solvers can be pretty good. So this formulation, the direct transcription, it gives you sparse objectives and sparse constraints. You have a bunch of terms that depend on a small number of decision variables, and the solvers can really leverage that with like sparse linear algebra. And this one, you've got everything's dense. And kind of, it just, it's less decision variables, but you've taken away the structure that the solver could exploit. Okay, and there's a few other things that, like for instance, if I wanted to write in there something like, let's say for all n, xn is less than 2. There's a wall at 2. I want to not run into the wall. Okay, then I've got to insert this big thing in the objective. I've got to insert it in the constraint. Every time x appears anywhere, I've got to take that whole big wad of things and drop it in everywhere in order to solve it away. properly. So, you know, if you have enough of these lying around it, it just becomes better to make a decision variable for it. Okay, but for the truth is, for when these are convex optimizations, convex MPC, either of them work great. When you get to the nonlinear MPC stuff, then it's going to be more problem dependent. Did you have a question? No. Oh, you had a question. Sorry.
Can you explain again how you took
Yeah. So what I'm just saying is, given x0 and u0, if I only make decision variables for that, I could write an expression for xn that's just completely a function of those other decision variables. So effectively, I can just remove these from the problem and insert that equation in every other one of those constraints. It's like I've done some pre-solve, said, oh, actually, I didn't need those decision variables. I can just solve them myself and tell the solver about those values and stick them right in here. Right? It's just noticing that I could simplify the problem in some sense. But it's, you know, simplify in terms of number of decision variables, but it makes each decision variable, each cost and constraint more complicated. Okay, so we've gained a lot. We can now do like constrained optimization. We have a richer palette. We've given up something important, which is we only solving from one initial condition. Maybe that's not a huge deal, right? Like, if I can solve these fast enough, you know, my robot's only in one state. I don't actually care about all the states my robot's not in. If I could solve these like infinitely fast, and if I'm currently in some state, then that's the only state I care about, right? So that's the idea of model predictive control. Okay, basically observe current state, or estimate, let's say. Solve, let's say, for instance, we've only talked about linear traj opt. And then I'll execute on my robot, send the command to the robot, just the first action. And then I'll let physics evolve my dynamics. I'll be in a new state. And I'll repeat. Okay? It seems a little excessive. Why would you solve for u n steps into the future if you're only going to take the first one? But because of these, sometimes you have to solve. In fact, in many cases, the whole point of optimal control is you have to look into the future in order to decide how to act in the first step. Right? So even though you're going to throw it away, you have to solve looking into the future, take the first action, and then update it and solve a new trajectory optimization on the fly. This is model predictive control. You would call it maybe the implicit optimal implicit MPC, which is the standard MPC, where you solve these optimizations, QPs, or linear programs on the fly. One of the big ideas in MPC that's important is this idea of recursive feasibility. So typically, one filters the optimal control problems that you write to make sure they have this important property, which is that if at time 0, I find an optimal solution, then I'm guaranteed at time 1, I will also find an optimal solution. You don't want to be driving along and suddenly your solver's like, sorry, infeasible, right? Then what do? So you really try to restrict yourself to, so, if you're an airplane that can prop hang or something, you want to make sure you always have a prop hang maneuver available. The simple, or a car that could just hit the brakes, that's not a great idea on the highway, for instance, but there are ways that you can try to guarantee this. If you're willing to admit, if you're willing to say your model's correct, then it's often easy to do this. You just say that the solution that I computed at the previous time step shifted by 1, you put a 0 at the end, is still, if you guarantee that that would be a solution to your new problem, you can guarantee recursive feasibility. So there's little tricks you do, like adding a final final state constraint that can help you get this. But that's typically a check you would want to do if you're going to deploy a model predictive control system.
That assumes nothing new is introduced, like a tree.
No tree that popped into appearance. Or if you want to be robust to that, then you have to make some assumptions about how that could enter into your constraints. Like maybe trees don't appear right in front of me. They appear at the boundary, and I have to have time to stop or swerve. So you can make modeling assumptions. It can put demands on your sensors and things like that. Yeah. Yeah, I think so. There's various ways to do state estimation. My favorite ones are basically trajectory optimization backwards in time. So if you've heard of smoothing-based, so typically you think of either Kalman filters, which are like LQR, or you think of smoothing-based state estimators. Those are just basically solving trad drop backwards in time. So they're the same. There's a duality there that makes them like kind of the same.
I'm imagining that if you're driving, say, down the highway, and you encounter someone working on the street or the highway, and the solution is not feasible, can you not just try to modify the entity so that it makes it less optimal solution, or finds a less optimal solution that is not just crash recursive, for instance, by adding
So you exactly captured it. He says, so I think the demand in recursive feasibility is you make some statement about how the optimization problem could change between time steps. In the simplest case, the variables just shift, but maybe you allow that some new constraints could become active or inactive. And you try to demand, like before you deploy this thing, someone needs to convince me that I will always have a solution to this problem when I'm running, given that assumption about the way the costs and constraints can change. Yeah, and so what you say about optimality, so the good thing about objectives versus constraints, objectives can be violated, right? So you can just sacrifice performance, but if you have real actuator limits or brake limits or whatever, then there's some things you can't give up. Yeah? That's right. So you want to say, I mean, it's reasonable to sort of say, at time 0, I found a plan. Yep. And then given that plan, yeah. And again, the idea is that I've computed n steps. So often the shifted by 1, the simplest thing would be to make sure that if I keep executing the original plan, that should at least be feasible. That's the way you get recursive feasibility. Okay. So I'm not going to get to tell you about perching, but I'm going to tell you about, I have to decide, I think I can't tell you about perching until the nonlinear extension of this. So I'll just carry the plane back. But next time. Okay, so how do we then take the nonlinear extension of this? Right, so let's do the nonlinear trajectory optimization. There's different ways nonlinearity comes in, or non-convexity comes in, but typically when I write that, I'm thinking of it as becoming now, I have nonlinear dynamics. Right? It could be that I also chose non-convex constraints or something, but if I were to take my direct transcription and change my linear constraints into nonlinear constraints like this, these in general are possibly non-convex. actually the direct transcription or the direct shooting, they both completely work. Okay, the math, the things I would write on the board are exactly the same, but the solver has to treat them differently because it can no longer leverage the convexity of those constraints. So it just implies that the transcriptions still work. But now it's non-convex optimization for nonlinear programming. NLP. So this gets to the pictures I was talking about in the optimization is if I'm just trying to, in general, if I want to min over x, f of x, g of x less than 0, right? The f could be arbitrary, the constraints could be non-convex. It's a much more general problem. Your guarantees are going to be less, your solvers are going to be a little different, but you can still write almost the same mathematical program. Like the code actually doesn't change very much at all. I just change my ax plus bu into just call my pendulum equations, whatever, and mathematical program understands it the same way, but sends it to a different solver. It says, I recognize there's some non-convexity here. I'm going to call SNOPT instead of Mosec or Garopi or something. So how do you solve these in practice? So mathematical program in Drake, we'll call a different solver like SNOPT, which is sparse nonlinear optimization. SNOPT is a sequential quadratic programming algorithm. Drake could have dispatched to a different one. The particular one it does by default is an SQP method. And the mental model you should have is, if I have some initial guess, then what SNOPT is going to do is it's going to make a local quadratic approximation by taking gradients and the like of my function, and it's going to jump to the minimum. And then it's going to take a new local quadratic approximation and jump to the minimum. And it's like doing gradient descent, but it's a second order method. It takes local quadratic approximations instead of just local linear approximations. And the reason we tend to favor that instead of just simple gradient descent, anybody know? Why do I like SQP over just gradient descent typically for these problems? Convergence rate, so that was, gradient descent might take lots of steps there, and you could take big steps with second order methods. You can converge quadratically. That's not the biggest one, actually. I would be okay. Yeah. It's possible it hops out of local minimum. That's true. But gradient descent, with a little momentum or something, could have done the same. It's the way it handles constraints. It more naturally handles constraints. Gradient descent, you can do projected gradient descent, and you can do games to do this, okay? But once you go to the quadratic methods, you're making a local quadratic programming approximation. So you take a quadratic approximation of your objective, but you take a linear approximation of your constraints, and you solve a QP on each step. So it's very natural to throw constraints at this, and even sparse constraints. It handles all the things that a QP solver would handle in the inner loop. Yeah. That's true. How does Drake know how to do that?
So I observed that you have at quadratic cost of that quadratic constraint, for example. So is it just like if none of that is used, it's like a general problem?
There's one other code path that we have. I'm not sure if Jump has it. I can't remember. Because the decision variables are actually, if you pass in a symbolic expression, they're symbolic variables. So there's actually some amount of, if you just pass in like x times y times whatever, then it will actually parse that and decide if it's linear or quadratic and send it, dispatch it to the right solver. That is not the most performant way to write a Koster constraint because we do some symbolic processing in the, but if you do pass in something like that, it can actually figure that out. It's a bit more like CDX in that way.
Right, right, yeah. But that will also be, like I would think if by default all problems are non-convex, and then if there is some, like recognizing non-convexity would be like
Non-elephants. Yeah, I get you. Yeah, yeah.
recognizing convexity.
Yeah, I think you're right. In the examples I gave you, it was either, so if anybody calls add constraint with something that is not known to be convex, it was either not symbolic or whatever, it was a general function handle, I just have to assume it's not convex. No magic there. Okay, so this stuff really works. Let me show you a couple fun examples here. Okay, so this is just a severely torque limited pendulum. Okay, like severely torque limited. It has to really sort of swing up and balance. Okay, which is a sort of impressively complicated trajectory it had to solve, right? But that's fine. It optimizes that most of the time just fine. This is, again, the optimizations are basically instantaneous. This is now the Acrobat swing up and balance. Just added a bunch of costs and constraints. Okay, and this is what, if you remember, my first promise was like we'd get better solutions to swing up the Acrobat. So it just does that, right? Most of the time. If like you change Snopt version 7.3 to 7.5, then I have to fix my code. There's a little bit of that going on behind the scenes, but cartpool. Again, the optimizations for these small problems are basically instantaneous, right? And they're doing non-trivial things, but from one initial condition. And if you were to look at an autonomous driving company or something, if you worked there for a summer, you'd probably see something about trajectory optimization down in the bowels of their planning system, right? And
So,
if you watch
um,
Boston Dynamics videos,
This is
you'll see them talking about trajectory optimization and model predictive control as being kind of the heart of what's making Atlas jump around. Right, so this stuff really works, right? We'll see they're making it jump onto boxes and stuff is more than we've talked about so far, but not too much more. We'll get there pretty quick. Cool. We'll do a little bit more next time.
So like you mentioned, they're not using RL for this.
Right, so they are, at the time of this talk, they were not using RL. I think they're certainly investigating RL